Hello everyone, how are you all doing? Hello Roxy, Alicia, Kat, Nan, hope y'all are having a great day. I now have a tweet with over 3,000 retweets. Like, 3,300 retweets, 600 quote tweets. How does lemma taste? I'm not sure, like, probably like silicone or something? Yeah, let's see. Gently slides into room, becoming a dormant, lurking pile of fried sludge. Fucking mood. Yeah, soft tum time. It is indeed soft tum time. As usual, compute. Yeah, tonight I'm gonna be playing a cool little interesting game I found recently titled Turing Complete. It is a puzzle game where you are putting together a computer from scratch with transistors and all. I am very excited. It's time flavor, clearly. Yeah, yeah. Lime flavor, yeah. 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 I'm excited. This is gonna be cool. Before I start, Kurama. Hi, Kurama. Don't think I didn't notice that you bought me a gift off my throne. Thank you very much. I really appreciate it. Yeah. With that, let's get into the game. I'm probably gonna have to actually, like, make a window capture for it, aren't I? Oh! Who grabbed that? Is it my Godot output? No. Like, let's do a window capture, not that. Turing complete. Okay. And up. Then I'm not sure if this game has, like, sound in it, so we'll find out. Name, game, play 1, Turing complete, and there. Alright. Let's play. Alright. Doesn't sound like there's music, so I'll just put this up. Congratulations, you have been abducted! We are testing you. The rules are simple. Build a functional computer or you will be eaten. Good luck. Alright. Signal flows from in to out. In the upper left of the corner, click input. There's a green icon. Right. Yep. So yeah, basically, click these, that'll turn input. You can click this to toggle input, then that'll change the output. Notice the out component is turned off. This is because signals stop flowing from the in component. We're very impressed with how well you completed the last test. We've decided that you are probably not a plant. In this level, the challenge is to figure out how the NAND component works. Be sure to figure it out before you complete this level or you get stuck on the next. I wish I was a plant. Alright. Alright, so. The inverse of that. Alright, yay! Nand Gates! These are functionally complete. You can implement everything with them. Theoretically you should use other gates, but that's expensive and takes time. Alright, now that you have a Nand Gate, it's time for you to build a circuit. Last level you made the table that described the circuit. In this level you're building the circuit that matches the table, okay. Alright, using Nand Gates, let's build a NOT gate. Alright, so drag from here. And for that you could just weep. Alright, yay! NOT gate. Alright, yay! Now we have a real NOT gate and level map mode. Ooh, okay. There is a lot to do here. There is a lot to do here. This is gonna be fun. Probably not gonna get through all this, but like, this is the working computer point. This game seems super neat, actually. Yeah, this is really interesting looking. Yeah, like, just, we are starting all the way from here, and we will be going all the way up. Or at least as far up as I can get in 3 hours or so. Might play this game in the future, too. Yeah, like, just, next up. Alright. Learn how to place components in circuitry while not destroying test equipment. Alright, so. We want, alright, so we want, a NOR gate. It's like if you made a game out of Ben Eater's videos, yeah. So, a NAND gate will work the same as a NOT gate, so 2 inputs. So, if both of them are off, we want a... Right, so... It's basically the opposite of a NAND gate, so why don't we just make the opposite of a NAND gate? I could just do this with a... Let me do this with a NOT gate instead, so... Then... Yep. Oh, wait. Ooh. Not what I want, actually, so... If both are off, NAND gate should be on. Yeah. Yeah, that's... Alright, yeah, so that's what we want. But there is something missing. So... We want it to only happen... when... Alright, so... Another opportunities here. Now that's an OR gate. So if we invert that. Oh. Now if I run. Woo! Alright, yay! NOR gate! Be apt to get to participate in glorious tests. Get a chance to communicate with very advanced people from the galactic civilization. Alright, so now we want an OR gate, which is the what I made last time but without the OR, so or without the last NOT. Boom! Woo! Okay, create the circuit that matches the table, okay. And gate time! Which is, not an AND gate, so... I think, personally, I think these should be, like, horizontally swapped, so, like, the AND gate should be on the left, then OR gate, and then NOR gate. I think that would make a bit more sense. Like, just because people usually go left to right on stuff like that, I think that would be, like, a good way to do that, like, to make folks experience better. Alright. Always on! This is easy. It's either signal or not signal. Woo! Ooh, a manual entry. Turns out that you can build all the logic for a computer out of either NAND or NOR gates. The Apollo guidance computers were built entirely out of NOR gates. Designed in the 60s, they had only 4 kilobytes of RAM and 32 kilobytes of disk space, but guided astronauts to the moon nonetheless. Modern computers are not built entirely of just one of the universal gates, but when applicable, NAND gates are preferred over NOR because they have less delay and occupy less area. Alright. Now we have access to true. As you know, these tests accumulate in building a functioning computer. Species that are capable of finishing are considered sentient by law. This is the main reason we don't eat you afterwards. Alright. Output on the second tick only. Ooh. I see. Ah, so ticks are just like going through like the logic table. So when only input 1 is on, okay. So this one and not the other one. Alright, good, 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 good. Woo! Tips! Woohoo! Yep. Tips! Yeah. Now, XOR time! Level is difficult, okay, so... Oh, tips, yeah. Are we designing a lemma? We are designing a computer, so we could use it to build a lemma. Now, here's where the fun stuff begins. So... boop, 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 boop. Woo! Online profile. When something is complicated, it causes a dilemma. Ooh. Truth tables! Tables of input and output, which are used everywhere throughout the game, are commonly known as truth tables. Input and output will often be represented with variable names, like in algebra, and instead of using colors, you'll often see the values represented as 0 or 1 or false and true. There's also a powerful trick one can use called a Karnaugh map, which will let you find simple solutions to truth tables. You may want to look up Karnaugh maps online. Onwards! Alright, so... bigger gates. Ho 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 ho! Alright, 3 gate OR! 3 gate OR! This is pretty easy. OR gate 1. OR gate 2. Go like that, yeah. Up. Up. Off. Yes, 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 yes. Woo! You are an AND gate with 3 inputs. Basically the same thing. Oh, you can move those too. Okay, neat. Tick. No, 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 no. Yes! Woo! Then, over here we got... Yeah, this is the first step before we get to arithmetic and memory. Create the XNOR gate, which is XOR not. Tick, 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 Alright. Now, who's ready for math? This level is my favorite pastime. And, yeah, I'm not, yeah. Converting decimal into binary under time pressure. Yeah. Toggle the bits in the level panel so they add up to the decimal number in question. Ooh! Oh, hey! Accessibility mode, nice. I'm not, yeah. Luckily this is not actually, like, super mathy. Yeah. Hey, Jude! Good to see ya! Alright, so... Right. Yeah. Right. Yeah, apologies for reading, so I've been lurking, yeah. Right, yeah, that's okay. Ooh, $109, Ah! Reach level 4 at least! Ah! Yeah, that did get a bit tough! Yeah, I'm glad that there's a timerless mode. That is good. Accessibility options are nice. Yeah. Right, it looks like accessibility options are just like from there, but yeah. So, then, double trouble. Because we are so technologically advanced, we have machines to fold our socks. Unfortunately, the circuit that detects sock pairs broke on the machine. This level has 4 inputs, output 1 when 2 or more of them are 1. Don't overthink this level. Can I unlock 3 Termans? I just want to unlock 3 Termans. Oh well. So... Oh. That's 2 signals. That's 2 signals. That's 2 signals. I'm gonna do you over here. Huh. That, enough? I don't think it will be, but... Oh, it's definitely not. But, luckily, I can add more Nand Gates. Because, whee-hee-hee, this is gonna be fun! Then just 3-term or there, 3-term or there, 2-term or there. tick, 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 tick. Woo! Don't overthink it. Optimization comes later. In our education system, we traditionally teach by tricking students into doing the wrong thing and then teasing them. That sounds like America. I'm not sure it benefits the students, but teachers love it. Create a circular dependency. This is a circuit where the input of a component relies on its own output. Yeah. In a circular dependency situation, it is not possible to determine the output of a component because you would first need to determine the input, which relies on the output, and so on, hence the circular. This state is normally not allowed in other levels, but in this level the goal is to create it so you understand what it is before going forward. So, let's just say boop, boop, there it is. Alright. A circular dependency is when the output of a component changes based on its own input. This game does not allow circular dependencies and instead triggers an error. One exception to this is that certain memory components are allowed to have the save inputs depend on their own load output. Circular dependencies can be very hard to debug. Alright, yeah. That is kind of important. Now we're gonna go do a bit of math for a bit. Using a maximum of 3 components output on only when an odd number of inputs are on. Ooh, alright, so there is a hint I can use if necessary. Okay. So I could use like the, I could do like the brute force and thing, but that won't fit in 3. So 4, yeah. Yeah, because there's, 1 or 3, 3. Wait. Or no. Tapped out, and this got complicated fast, yeah. Yeah, we are trying to detect if there are an odd number of signals, on. Yeah, so, and I've got to use like 3 components or less, so, where is the icon? I'm not actually sure where, like, the hint icon goes, so... Ah. Yep. You can figure out if 2 components have an odd number of, with just 1 component. Oh, so XOR gates, okay. Yeah, so... Oh. Would it really just be 1, 2, 1, 2, 1, 2, 1? That it? Tick, 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 tick. Wow, okay, that's it. Wire color, hell yeah, and wire comments. Woo! Onwards. Yeah, yeah, we got through like all like the basic gates and such, and then we did like mathy stuff. I did this mess, which is a bit much. Like, no. Map, okay. Yeah. Yeah, we're doing arithmetic and memory right now. Components needed about 20. The solution for this level is not very neat and requires more components. Woo! Arithmetic and memory, my two best subjects. Dubious disgust. Mood. Okay. Let me look at this one first. Yeah. Alright, now we're actually like... Yeah, this one will actually like... Yeah, it is weird that it is like the easy... Or like the introductory ones are always on the right hand? That's just a bit weird, TBH. Like, just a weird, like, pattern. But yeah. Let's... Yeah. Treat the inputs as 0 or 1, depending on their off or on. Add them together in binary so that the result is either 0 or 1. With normal addition, if the result cannot be described with one digit, set the carry to 1. Okay. So, this is how to do, like, a 2-bit single counter. Alright, so that will be our sum bit, and then the carry bit will be a 2-term AND. That tick, 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 tick. Woo! Brain companion, okay. Motivation plus 38%, onwards. Alright, so that's how you do a counter. Okay, this is going to be a lot. Okay, so it said about 20. So, we know how to make a, like, terminal, like, with carry. So, let me just quickly, yeah, if I check, so you're, that's 1, okay. So it's 1, 2, 4, okay, so going to do an XOR. Yeah, we're going to do the XOR AND pair. Also, I want this to be a... Alright, so... if a single one is on, that should just result in 1, okay. I am gonna, like, just... So... we will need a counter, ultimately. Or, like, yeah, we'll need to, like, add together the signals. So, like, just... Alright, so... yeah, so what we're gonna do here is, since there's a total of 4, we're gonna have... or, there's 3 outputs, so we need to have these. Okay, so... And that should feed into another XOR AND... for 4. Alright. I'll just put this one in pink. Thank you for the hydrate posture check, Jude. No, and Gate goes back. Wait, no, that's supposed to be an XOR gate. So, be like just watercolor there. Grab a pink. So we've got 1, 2, and those those should go to the same one. Yeah, this is, I'm gonna pull up the hint. Circuitry for the 1's bit is the same as what you did for odd number of signals, okay. Signature for 2 bits, is what you did in Double Trouble, except when all 4 are on, okay. Then we can, like, use the counter. So... Is there a better way to do the odd number of 1's than I did? Or odd number... Yeah, so odd number of 1's is XOR, XOR, XOR. So that's the 1 bit. I'm gonna pull you up here. One, 2, 3, 4. Okay. So there's the 1's bit. Yeah, so like just, yep, so that's on. Alright, yeah. Oh, can I? Oh, it just stops it, okay. Oh wait, no, I can just flip them over here, right? So... Alright, there. Yeah, alright. Then 2's bit is if there's... Alright, so... I should yeah, so 4's bit is just gonna be... I'm gonna do you in another color. You'll be in green, so 1, 2, 3, 4. Around this way. There. Alright, so yeah, there's that. And, I did something really bad for And, didn't I? Or yeah, for Double Trouble. This... Oh. Is there... Okay, yeah. It says don't overthink this level. This doesn't feel like the best way to do it, but it might be. Yeah, this just feels ugly. This doesn't feel right, you know? But, if it is, it is. Yeah, circuitry for the 2-bit is... 2-bit is... Oh, circuitry, for the 2-bit is what you did in Double Trouble, except when all 4 are on. Oh. So... yeah. Alright, I'll just do the bad thing. I need to pull these down, don't I? Oh. Oh yeah, so... I'll go down and around. Okay, you're just gonna do that. Then let's grab another color. Yeah. Alright. Wires are crossing. Quite literally. And... 3, 2, 4, 3, 4, and I need 2 3-term OR gates. 1, 2, 3. Then an OR for that. Then an AND. And there's not enough room there. You go 1 click back, okay. Okay, now 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 1. Tick, tick, tick. No! Shit! Why? Not gate. Tick, 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 tick. Tick, 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 tick. tick, tick. Fuck yeah! Ah. Oh, I'm proud of myself for that one. Ah. Numbers you're used to are base 10. Here when we add a 0 to the right hand side of a number, its value increases tenfold. Binary is base 2, so doing the same will instead just double it. In other words, each digit represents a power of 2. Bit of a peek on the fuck there just to note it. Yeah, that was me getting, like, excessively loud, but yeah. Oh. Need to figure out my audio situation better sometime. Yeah, for example, with base 2 and base 10 color-coded, 1 equals, yeah, 1 equals 1, 1 0 equals 2, 1 0 0 equals 4. To represent 6, we can simply add 4 and 2, 1 1 0 equals 6. Yeah, addition, multiplication, and everything else works the same as base 10, except you carry when you reach 2 instead of 10. Onwards. I am honestly, like, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 nodes. Not bad at all. In the previous level, we added together 2 inputs. This time, we add 3. Once again, add the inputs together in binary such that the result is either 0 or 1. As with normal addition, if you can't describe it with one digit, carry to the 1. So... Alright. We can just set up the XOR AND again. Oh, good turn. So, up, 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 up. Goodness, he's lurking down to my support group. See ya, Roxy. Alright, so... that satisfies that. That, okay. That, alright, so we can tick. Oh, because I haven't wired them. Oops. Yeah, yeah, those ones are good. Now we just need to do it, now we just need to... Would I do an XOR AND with the output of that? Future AND. So that would just be... Would that be correct? Tick, tick, tick. No. Tick. No. Yeah, so that should be, some... Wait, do I just swap the AND and XOR? That's a 3-term. No. No. Both XORs? No. So, if you have 0, 0, 1, the sum should be 1 and carry should be 0. But, yeah, so carry should be 0 if, you know, like, in this scenario, so... Yeah, so... That's good. That's not, because... Some that should fire a carry. Rigging the... Yeah, so... 1, 2... 3, 2... Yeah, so that works. But I need to figure... So, like, the carry should be... The carry is with 1 and 2... 1 and 3... 2 and 3... Or 1, 2, and 3. I could, like, hard code that, but that doesn't sound graceful. That sounds very non-graceful, and I don't like that. So, 1 and 2, but not... So, 1 and 2, not 3. Or, yeah, so... So, that would be 1 and 2 or 3. Yeah, so that is 1 and 2 or 3, 2 or 1 and 3, and 3 and 1 or 2. And it has to be any of those, because... Like, this, no. Yeah, and that's like the fail state for it. I could also just, tick, 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 tick. Oh, okay. Now it does it for me. Is this right? no. So that's okay. Oh. Oh, I'm actually very close, so... XOR and or... Oh! All I need to do is... route that. Okay, that's it. So, I just had one excess gate in there. I didn't need the OR because the XOR is already basically doing that job. Alright, nice! Haha. Yeah, there are a couple other... yeah. There are a couple other ways to do a full adder, but that's a pretty elegant one, I think. The input and output of this level are using bytes instead of bits. One of the two new components you're given takes a byte and splits it into bits, and the other does the opposite. Using those components, figure out how to double the input number up to 127. Okay. Byte maker, byte splitter. That's easy. That's called a shifter. Woo! All right. Bytes! This game will ask you to build an 8-bit computer. Practically, this would normally require the player to put down 8 parallel circuit lines in as many places. To alleviate tedious busy work, you're given the notion of a byte, which is just a virtual bundle of 8 bits. The state of either a byte input, output, or circuit line is represented by a number instead of the red or green color. Alright. Onwards. So... alright, bitwise! Woohoo! You may think it's unethical to eat all the earthlings that don't win the competition, but it's actually okay because you live good lives in the wild and we don't let the meat go to waste. Alright, bitwise ore! Bitwise ore! That's one of you, and one of you. And do you know what bitwise OR means? That means 8. Yeah, 1, 2, 3, 4, 5, 6, 7, 8 bits. Pairwise, yeah, it's bitwise, but yeah. 1, 1, 2, 2. I'm just gonna use lemon green for this. 1. And this. 2. 2. 3. Oh yeah, no. 4. 3, 3. Bit 4. Bit 4. Bit 5. Bit 5. Bit 6. Bit 6. Bit 7, bit 7, bit 8, and bit 8. Byte there, byte there. 1, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8. Output. Tick, 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 tick. Woo! Bitwise OR! Bitwise not, okay. One. 2. 1. 2. I'm actually gonna 2, 3, 4, 5, 6, 7, 8, and I'm just gonna pull these up further. Yeah. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Ouch. Woo! Bitwise not. Bit adding, oh boy. Add the 2 input bytes. Each output bit in the output should be the result of the addition of the corresponding bits from the inputs and potentially a carry. The result does not fit in 8 bits. Turn on the carry output. 9th bit, okay. Input carry as well. Useful for training together byte adders. You can think this carries a 0 or 1, okay. Hint if you get stuck. Where's my bitwise? Oh no. Wait, I just... Wait. Do I not get the... Yeah, byte or, okay. Do I just not get that for this level? Ah. I mean, they are on the same tier, so yeah. I think this is gonna be, like, effectively 8 full adders. Should be fun. 8 staggered full adders at that. Okay, so I think this is... Okay, so time to, like, restructure stuff. Alright, I've got 2 input bytes, so... Gonna need another splitter, okay, so... Beep, beep. And you'll be aligned here. Beep, beep, beep. Beep, beep, beep. Beep. Beep, beep. 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 Now, 1, 1, 2, 2. I'm actually just gonna drag these off. 1, 1, 2, 2, 3, 3, 4, 4, 5. 5, 5, 6, 6, 7, 7, 8. I can draw that one correct. 8. I can draw that one correct. I'm gonna go down by... Okay. Woo! Fight adding! Yeah, this is like... Yeah, this is honestly pretty cool. Yeah, just like the fact that we've made these full adders. We've, you know, like the splitter is just like a shorthand, but like we've made all these full adders. And now we're like finding out how to like do like higher sizes with them, and that's really cool. Tangle Gates. You must depend on you just learned how we won't allow circular dependencies. Now you must learn the exception. In this level, you must build a set reset latch with which stores memory. This is the only level in the game that allows circular dependencies. RS NOR! RS NOR! RS NOR! Woo! Okay. Consider this simple circuit just 2 NOR gates in a row. And this magenta wire doesn't immediately change anything until we turn the input. Notice blue wire is now on, or no, is now off. Remains like this even if after we turn the input off again. We're now trapped in this new config. Looking at the blue and magenta wires, pretty clear that only one of them can be on at any time. Turning one on turns the other off. Finish the circuit such that magenta wire is connected to output A, blue wire is connected to output B. The first input toggles the blue wire, the second input toggles the magenta wire. Alright. I'm just gonna tick through that, so... Alright, set. Alright, off, reset. Off, set, off, reset, off. RS NOR latches, cool! Now, we've got one, so we don't have to worry about that. Just like, this is a, hey, keep in mind that this is what's going on under the hood, which is neat. Turing complete. Certain computers, like simple calculators, are limited in the algorithms they can perform. They cannot perform any calculation that requires looping or recursing an arbitrary amount of times. Technically, machines without looping or recursion can only deal with combinational logic. Turing-complete machines, on the other hand, are as powerful as it is possible to be. A Turing-complete machine may have a slow CPU, but it is powerful in the sense that there is no computable algorithm it can't perform. Basically, Turing-complete means you can run Doom on it. It may take forever, it may not have enough memory, but if you give it enough memory and enough time, it can run Doom. Alright, saving gracefully. The set reset latch contains, one bit of information, but in a manner that's not very easy to load or save. Create a circuit that can save one bit of information. The first input should determine if we load or save. The second input is the value to save. This value should be ignored if we load. Make sure you understand how the set reset latch works. Think of what the truth table for the input to the SR should look like to complete this level. Alright. So, if we load off in or save on, it's like just So yeah, right, so A, yep. so A and not... Alright, so those are A and not A. So... I1, I2, yeah, so... Let me... So... Let me just hook these up, so... So that... It is just a toggle, so... So if we save the value... Alright, so we're gonna have... Okay, so... No. Do I want... Oh. Oh wait, so that's like just... They recommend we keep that, I think. Yeah, so that will always toggle it, okay. This already hurts my head. Hello, Nikki, yeah. You are, like, a bit late. This is, like, already, like, decently down the line, but yeah. That will always... Right now I have it configured, so it will always be the opposite of that. Now, do I want an AND gate there? So, like... No. If I save... Alright, if I save one... This hurts my head too. We should have it so if save and value, okay. So that should be, there should be an and. Did you see the new model update? Not yet. Let me take a... Ooh, looking good. Ah, looking stellar. Alright, so... you should be, you should be like that. Yep. No. You need both that and, okay. I'm getting a feel for this. I'm getting a feel for this, so... Already. Oh, because I didn't wire that back. Safe. Alright, good, 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 good. Wow! Okay, that's 1-bit memory. I'm just gonna clean this up a tiny bit so not goes right there. But yeah, I didn't expect that to work first try. Or like, not first try, but yeah. Did Nikki get a new model? Nikki is getting a new model. Yeah, hello, Katten. It is great to see ya. I'm learning how to make a computer. I apparently just, like, yeah, I managed to figure this out. So, yeah. Yeah, I'm honestly, like, surprised that I got this to work. So, like, if all of them are on, it'll set the set reset gate on. Then if we turn that off, and turn value off, it isn't able to clear it because the input is locking, yeah, because the load save toggle is blocking that. Then turn load save on and have the value off. It can reset that. Tick again. That can't, yeah, that's blocking that from it resetting. Yeah. That worked! Day 6.0 is coming along for the new year. Gonna be a Rebellion theme. Yeah, I cannot wait, Nikki. Ah. Alright, so now we've got bit inverters. We got switches and negative numbers. Oh boy, we're gonna learn 2's complement. We're experimenting with how backgrounds influence cognitive functions in Earthlings. Alright, when invert is on, output the opposite of value, otherwise output value as is. Okay, this is pretty easy. Yep. So we're gonna have an AND path, or a not path, so when invert, yeah, so that's gonna be along here, so this will just, yeah. Okay, let's see, so when value and not invert output, okay. So 1 and not, okay. That's just an XOR gate! Or no, it's not. Is it? Yeah, that's just an XOR gate! Despite the funny background, you figured out this was just the XOR gate in disguise. Well done. Sorry if I clipped there. Yeah, no, that's just a 1-bit inverter. You know, like, a toggle inverter is just an XOR gate. Okay. Negative numbers. Oh, this is a math challenge. Oh boy. 2's complement time. Get subtraction. First we need negative numbers. We need a way to have negative values in bytes. The scheme we've been using so far can represent all numbers from 0 to 255 using a byte. This scheme is called unsigned since it only deals with positive numbers. One's complement. We need a scheme that allows for negative numbers, normally referred to as a signed representation. Additionally, it would greatly simplify future circuits if the representation works with the adder you already made. Alright, continue. Change what each bit means by changing the numbers. Toggle to see the result. So... Alright, yeah. Now I'm confused because I don't see circuit parts. Yeah, this is like just teaching you how to do, 2's complement, or like how to treat 2's complement. Which is just, the last bit is effectively, yeah, negative 120. Like, you can treat the highest bit as negative 128. How about base minus 2? Oh no. Yeah, the way to represent negative numbers you discovered is called 2's complement. It's the standard way to represent negative numbers in modern computers. The main advantage of 2's complement is that the negative representation works seamlessly with the same adder that we use for the non-signed representation. In the early days of computing, the main contender to 2's complement was 1's complement. Its main advantage is that changing the sign of a number is simple. You just knot each bit in the number. However, it has 2 representations for 0, a positive and a negative, which makes comparisons more difficult. Another interesting representation, perhaps worth looking up, is base negative 2, where the sign of the value of each digit alternates between positive and negative. Yeah. Alright, switch. Create a component that switches an input byte on or off. To a transistor? So, output... Oh, it's out... Yeah! A transistor! This is a transistor. Hello, sun roses! I am making a computer. Hi. No. So, 1, 2. I'll pull them from this side, yeah. 1, 2, yeah. This game looks cool, TBH, if you can call it again. I mean, it is absolutely a puzzle game. Yeah, it is very cool so far. Like, it is teaching you how to, like, make a computer. Here. Where can I get it? It is on Steam. Let me link it. When's the puzzle up? Lets you run Doom. This is sadly a 16-bit computer, so it would take a very, very long time to run Doom. But it is Turing complete, so it technically can if given enough time and memory. Woo! Switch is by on. Wish listed, yeah. Pregnancy test can run Doom. Yeah, look, so that pregnancy test can run Doom thing, that I followed, I watched Foon write that thread out. What Foon did was put another, display inside the pregnancy test. The pregnancy test itself did not run Doom. You can run Doom on a lot of very silly things, though. Like, any, 16-bit... Technically, it's technically a Doom viewport, yeah. Alright. Input selector. Even though he did not pass our test, we decided to keep the dog. Unlike most Earthlings, he's fluffy and follows simple instructions well. You might want to team you two up, since you complement each other's shortcomings well. When the bit selector is off, output by A, otherwise output by B. Okay. That's switch. Yeah, this is pretty easy, so input selector is that and that. I'll wire this one over here, okay. Selector, and not gate, so go. Oh wait, we probably want a... That bit splitter was frightening, yeah. Can I use that? Wait, I accidentally hit both of them to that. Whoops. I think I can use these for Bitewise now. Or actually, no, I think that's still a Boolean, so... You go like that, and then not gate here. Ah! Oh wait, did I? When the bit selector input, oh. Might have it backwards, yeah, I think I have it, yeah, I think I have it backwards. Yes. Woo! Mux Gates, okay. Sign negator. Taking the input as signed, where the 8th bit is -128. Thank you for the hydrate. And a stretch. Make a component that takes a number and negates it. For example, 4 negated would become -4, -9 negated would become 9. Cute. Nope. So yeah, wait, this is a not +1, yeah? Yeah, this is not +1. Woo! Negator! Yep. Not X+1 yet. Okay. And over here, create a circuit that can save or load a byte. When the first input is on, load memory and send it to output. When the second input is on, save. Okay. So we've got 1 bit of memory, but we want a whole byte, so that means lots of them. Alright, so oh, alright, so self-dependency, got it. Yeah, so rising edge and falling edge, yep. Seven, 8. Then we're going to want a splitter to go to all these. Which, alright, yeah, that goes to the lower bit. 2, 3, 4, 5, 6, 7, 8. Yeah, so what we're doing is save or load byte, okay? We're gonna want a recombinator, okay, so why are there 2 attachment points on the end? One is the, yeah, so it'll fire a bit to, yeah, so it'll fire a bit whenever it wants to save, which is the save enable. So that's the load pin, that's the save pin, so that should go to the enable pins. You can use the switch for load enable. How do you load? Do you have to clear the output if it's not requested to load? We'll see. Alright. I have apparently got it correct. So only when, like, the load pin is enabled, it should go through. Yeah. Alright, yay! We've got a register! Woohoo! Ah! Yeah, I just made a byte register, and I am incredibly proud of myself, honestly. Like, this is a register. Ah. Congrats. Posture check, thank you. Ah. Alright. Woo! Next up, create a component that can switch a signal between 2 pins. Alright, oh, this is bitwise. So this is just so when out yeah, so that'll be out 1. Pull that up. No! Flipped it. Woo! Alright. Decoder! Is this a DMAX? It's a decoder. Didn't you made it SWC? Yeah. Yeah. Yeah, this is, DMAX, yeah. Confusing Mux with DMAX. Ah. Alright, so... Then, 3-bit decoder. With 3 bits of input, there are 8 combinations. Make a circuit that selects 1 output for each of the 8 combinations. No more or less than 1 bit should be on at a time. Ooh. Okay. So this is how... Gotta go, love you. Love you! So yeah, this is when we start doing fun stuff. So... Now we do... Yeah. So this is... Yeah, now we're decoding a 3-bit signal. Okay, so... Yeah, so this is just a pretty basic decoder, so yeah, I just need to figure out how to do that. So I think we want to do this. I think we do want to split it with 3 decoders first. Like now, yeah. So 1, 2, 3, 4, 5, 6. Huh? 4. Yeah. Trying to, yeah, like, trying to figure out how, like, the best way to do this, so... Yeah, so that's 6, but then we need to do some combination stuff, so... If that's... So 1-0... yeah, so 1... So 000 should go up here. Which should be a 3-wise NOR, yeah. So like a 3 or not. Then you should... Think you could just use decoders? To get, like, the 8 there? Maybe, yeah, Trying to figure out how that would work. Since each decoder can only have 1 in and has 2 outs. I am decoding here, just... Here's a question. Probably wrong, yeah. I'm trying to, like, just... Yeah, I think so, So a NOR gate... Yeah, so a 3-wide NOR gate for these. Then... And for all these. Now that's 2-bit, so... Oh no, those should both be ands. Not... Those should both be 3-way ands, yeah. Yeah, so that turns that one on. That turns that one on, but that is, like... That would take 8 AND gates, and that just doesn't feel elegant. You could use Mux Demux? I only have byte level Mux is the thing. Yeah, this is all bitwise. Yeah, that is like kind of I remember seeing like someone do this in Redstone once. I just don't remember how. Just gonna pull these a bit closer, so yeah. This splits these signals out. Come on, ear, you can stop ringing now. Yeah, that gives 6 signals. I can do this with 8 AND gates, but that just feels inelegant. Is there a hint on this? Yeah. So... Something about binary trees? Yeah, So... I'm gonna try, like, the inelegant solution for now. Then I'll, like, I'll look up how to do this afterwards, so... You should be in your top. Bottom, top. Up. I should not be doing all these in the same color. I'm gonna color code them by byte, so you're just gonna be, I'm just gonna put these in, like, the base wire color. Colors, yeah. You've got colors in this game. Pretty cool. So yeah, then let's say, so for the first one, you're gonna be top. Alright, so that's off, off, off. Then on, off, off. Off, on, or, yeah, off, on, off. Then on, off. Number 5 is, yeah, alright, so you're gonna be off, off, on. Number 6 is gonna be on, off, on. 7 is gonna be off, on, so off, on. And 8 is gonna be on. Tick, 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 tick. We had our intern add a disable bit to this component. We were tired of looking at him running in circles and we're looking for other pointless and tedious tasks to give him. Right. 3-bit decoder. Let's look at... Are you fucking kidding me? Never Feral TBH, yeah. Is that's the canonical way? Yeah. This is what you do for a 3-bit decoder. Some folks have used, like, Nand Gates and such, but why? Yeah, no, this is how you do it. That's like the, yeah, it is inelegant, but that's just how it's gotta be sometimes. That's why you never look at those again. Ooh, manual entry. Counting is so fundamental even insects can do it. From counting, species can evolve to compare and do arithmetic. And before you know it, you have apes building computers. Make a device that counts increments once per tick. Build a counter which will increase by 1 each tick. Additionally, there should be an option for overriding the counter with a given value. You're given 2 inputs, a bit and a byte. The bit input should toggle between counting and overriding with the value of the byte. Okay. Register time. So... then adder. Need an always on for this adder. Alright, so we're gonna use a mux. Yeah, so gonna need a mux here. Okay. So when input is on, it should use number 2. I'm gonna quickly switch back to my lemma green traces. There. Yep. Nope. Right, Right, I need to have one to the other. That's what this is. I've got a carry flag for that. Hmm. Yeah, the counter... I'm trying to figure out, like, the way to make it increase is, like, the big thing here. Like, I've got an adder +1. Like, just that's going around properly into the muxer, which is going into, like, the save value. When do you save versus load the register? You're supposed to, Oh! I got it! Alright, you just have save and load hotwired all the time, okay. Counter! Self-dependency, yay! Alright, can you fit 4 bytes of memory in this limited space? Circuit that can save or load from 4 different bytes of memory. Given 1 bit that determines if you're... Alright, so you've got 1 load toggle to a load... Alright, we're making a 4-bit register. 2 address bits. Oh, spacebar rotates, okay. Alright, so we have a tiny amount of space. We got, Alright, cool to know that we've got rotation. We've got, Right, so I'm gonna have 2 decoders for each of the address bits, okay. And 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 so... Not quite what I want, so... So I do need... I know I need 4 registers. Like, that, like, just is, like, what this requires. Fundamentally. So... Reg... 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 Now I need to, like, select... Alright, so... We've got... That's load bit, save bit. Switches? Alright. Maybe switches after? It's just like, the switches need to be determined... Oh. Yeah, I think I'll need switches after too, so... Yeah. Y'all need to go there, okay. I'm actually gonna have... Whoop. I think I should start color coding, so... Hot wire... Alright, so that just goes right to that switch. Right to that switch, right to that switch, right to that switch. I'm gonna have you be in blue. Okay. All right. Then I'll have pink here. 1, 2, 3, 4. And now, here comes, like, where I've got to do, like, the signal stuff. So, I've got decoders. Alright, so I can have... Yeah, alright, now I can have 2 decoders. I'll put those on purple. I'll move them a bit further to the side, so... You have 2 decoders like that, you might end up modifying 2 bytes at once. Yeah, no, that, like... Yeah, Do I need decoders for this, actually? So, I could have... So, I need 1 and... 1 NOR, so... 1 is gonna be an AND... 1 is gonna be a NOR. Ah. More colors? Yeah, I think I can handle without. Then I need then I need 2 and knots. So, not... And one more, and not... Ah! Ah! Not sure why cop sirens are going on. Okay, so... I'm not actually... So, expected output 145, but... Here... So... Stop. Alright. Something's going on outside. I have no idea what it is. So, alright. Right 94. So right 94. Load. Good. Right 47. Alright. Right 47 to B0. Load. Right 145. Load. Right 177. Load. Load A1, it lost it! No! That's the issue. Oh no. Ah, oh, boy. This is not good. I need to clean this all up real bad, so why don't we just do that first? How do I, like, use a hint? Rolls. They're like, yeah, I'm not sure how to use a hint, actually. Are there hints? Yeah, theoretically. So, thinking you could use byte switches instead of bit switches, but I forgot why. Yeah, I can, yeah, like, switches are 1-bit toggle, and then you can just pass through like that. They're, more like a relay than anything. But yeah, yeah, so, like, that's a relay, basically. Just need to, yeah, like, that'll relay it, just like, Instead of, like, the thing is, I think what I need to do is, instead of, like, having the signals connected to switches like that, I need to connect them to the save and load. And then have, yeah, so I do still need switches, but they should only need to be on like, the output? Let me just experiment with register quick. So, save, load. Oh, alright, hopefully everything's alright. Yeah, then load. Okay, so, oh, that actually makes things a lot easier. So I only need to worry about signaling on the save and load. So let's grab some registers. 1, 2, 3, 4. one by one. Okay, so now now I need to make those like latches, so decoders might be what I want to use here. I think so, yeah, I do feel like decoders are what I'm going for. Then I'll need some, and I think I'm gonna need... Yeah, then I can use... Theoretically, I should actually, probably use... So I'll have 4 Nand Gates for signal. I should probably have, like, moved a couple closer. Maybe, like, ones. So now I need off, off, on, off, 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 on, on. Then use a couple of these down here. So oh dear, there's not enough room around back, so... Oh dear. Alright. We often like having ADHD, but this is just one of those sorts where we could wish our focus brain could just not tangent. Oh, I get that. Real bad. Oh, wait, I can just bring it down here. Can't I? So here's the load bit. What, I can't use that last... Having this little space makes things very difficult, so... What I'm gonna do is... I'm gonna multi-select all y'all. Alright, so that's as far down as it can go. This is as far up as it can go. Now I can... You can stack Twice as much as you want, right? Yeah, but that gets really hard to manipulate, is the main issue. So these are more... You're gonna be off, on, and you're gonna be on. On? No, you're not. You're gonna be off, on, on, on. Ooh, you can move the inputs. Yeah, you can move the inputs. So that's what I did over there. So now I've got, and I'm gonna make you, so load is gonna be this color. Ugh. Trying to figure out, like, how to make this tight. I think it might be better... So... I'm gonna have these up here. Could you use 1-bit mux instead of it? No, you can't. Yeah, I don't think I can is the issue. Yeah, just like, I think what I ultimately want to have is like 8 AND gates. Yeah, like 8 3-way AND gates. Which there's not enough room for. Wow. Didn't you do that already? No, I had things set up so they would use 12 2-pole AND gates, which just won't work, really. I can just, like, stagger it. That'll make that east. Yeah, that'll make that work, so... Now I'm gonna do some... So... Alright, so that's... Oh. Save. Oh. Load. Yeah? Load. Actually, no, those... Because of that positioning there. So, first off, I've got to make... so I'm gonna make some... Because this is right here, so I need to... What I could do is... I can just rearrange these to be a bit more... I can align them like this. Thank you for the hydrate. Right. Ah. Okay, so now we can start doing fun stuff. So you're gonna be as far up there as you can. You're gonna be pulled down just a bit. So let's say, alright, so green is gonna be 1, 1, 1. Signal. Ah. There. And I don't love you. See ya. One, 2, 3, 4. And you in, say, blue. 1. Getting my colors confused. 2, 3. Back over to you. There. It looks organized, yeah. Ah. Right, then you are gonna go... Wait, if you're the save pin and then... Oh, look, save is... Okay, lower, so yeah. Save. Save. Yeah, save load, okay. Save. Load. Save. Load. Save. Load. Color warning yet. I'm just gonna have like all those route. Then I'm gonna... And then I think... So then... 0, 0 should be all the way over here and all the way over here. Then yeah, Yeah, I'm actually gonna... You know, actually that's fine, yeah. Color as it is fine. Yeah, so that's fine, okay. Okay, so then more wires, so... Oh, you got deleted. There. And... You're A, so then we'll have... No, I see what's going on. Okay, so... One, 0, 1, 0. Then, if this works, tick, 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 tick. No. Stop. So tick. Right, save 94. Good. Load. Save 47. Load. Save 145. Something is wrong. You. That. Save. Load. Save. Wrong. Time to redo that all because I screwed up somewhere. Yeah, so I'm just gonna do it in like color pairs, so 1, 1, 1, 1. Okay. 1, 0, 1, 0. Zero, 1, 0, 1, 0, 0. No. 0, 0. Tick. Save. Load. Save. Load. Save. Load. Save. Load. 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 Save. Save. Whoa! Think you took twice from the fire pin for the fire? Nope. Guess I'm wrong. Yeah. It just the colors just overlaid each other. In our advanced civilization, forcing prisoners to do extremely menial tasks is slavery and is technically illegal. That's why we instead had our intern create the 256-byte version of your component. RAM! Woo! I've got 256 bytes of RAM, fuckers! 8:33 already, and we're not even done with arithmetic. Almost, though. This level starts with two special components. They simultaneously act as input and output. Make sure signal flows only from left to right. There are 3 tests. Test 1, both sides will be red. Test 2, left side will turn green and right side should be green. Test 3, right side will turn green and left side should be red. That sounds like a job for a diode. Diode time, yep. 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 Woo! Buffer! AKA diode. Alright. We are done with arithmetic and memory. It's time for CPU architecture. Let's go. Create a device that can OR, NAND, NOR, or AND two inputs. The third input will be the instruction. Who's ready to make some assembly? All right. You don't get, it's sometimes, so you don't get to pick one, so it's not Java SM. You get to make, like, look, later on in this, we will be making our own assembly. Which is the coolest fucking thing. Okay, so. Ooh. Cinemax, thank you very much for the host. So. Nand and, okay. That's NOR. So we're gonna take and we've got to get a byte splitter quick. Byte splitter. Alright, so there's and okay. Alright, there, that's good. Now we need a NOR. Bitch. So there's NOR, okay. Gonna be an and not. Ah. All right. And we've got and NAND, okay. Do we have, like, I don't have, I don't have a bitwise NAND, do I? I'm at least gonna make and shift this. So let's see. So actually, you're gonna be up here instead. Gonna have a not gate here, then just a plain. Okay. Okay, so theoretically, that's all we'll need for that, so... Did I not move you? Oh, boo. Okay. Second, and double dip first wire? Guess that's the first and, yeah. Second and double dipped first wire, it did. Thank you! Okay, so... Am I just gonna have to, like... So I can just do a knot for that. Now, okay, because I'm gonna have to do a bitwise and... Which is the last one, actually. That's gonna be fun, so... Let's get some... Let's make a splitter. 2 splitters, actually. Because, of course... No, or so small compared to and, yeah. That is mainly because... And I'm gonna need to make a maker. I'm gonna have y'all go here, actually. Alright, so there's that. Now I just need to actually put in the AND gates. Okay. So, 1, 1, 2, 2, 4, 4, 8, 8, 16, 16, 32, 32, 64, 64, 128, 128. Now, hook them up. Yay, alright. Check. 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 No! This is wrong, so... This should be ignoring. Who is... Oh! Forgot to wire up the NOR. Whoops. That might be a bit of an issue. 1, 2, 3, 4. Alright, yay! Onwards. Alright. Time to create your master project, implementing the Overture computer architecture. This will be an actual Turing-complete machine. I've locked the red components of this level in place since you always make a mess and don't leave enough space. The mess you make from now on is saved between levels, so you no longer get to start fresh each level. Oh boy! In this level, you need to create a circuit which can copy from a source to a destination. The instruction byte in this level determine the source and the destination. Beep. Hello, lovely mimic! Bits 1, 2, and 3 give the destination, bits 4, 5, and 6 give the source. Source and dest can be one of 6 registers. We'll name them Reg0 to Reg5 respectively. Additionally, this map has a dedicated input component which can be the source and an output component which can be the destination. Alright. 1, 2, 3, 4, 5 input and unused. 1, 2, 3, 4, 5 out, unused. Okay. Input and output now have an actual pin. Set that pin when you want to read from input or copy to output. So, instructions, okay. Okay, so actually, back to level map. Is this the, or oh, yeah, that's a lot of space. Yeah, this will be the that's a lot of space, but this has to fit the entire computer. So, instructions, alright. Alright, so it's time to... Alright. We're gonna get some, 3-bit decoders. So, 3-bit decoders, and we're gonna need some splitters. Okay, we're gonna have a splitter here, so... You pick, so... 1, 2, 3. Then we need another splitter. So 1, 2, 3. Alright, these are... Those are unaffected. Okay, yeah. 3-bit decoders, yep. And here's the value which I can't move, okay. And the out, alright. Okay, so... Now we need some switches, so we'll need a lot of switches probably. Yeah. We will have work RAM at some point. Yeah. Don't think we'll need that for a bit, so let's see. So we've got switches, we've got counters. It's a lot of RAM low, yeah. So here's the fun thing. So we need to link this . 3, 4, 5, 6, and out. Buffer. Just got that. Where? Please tell me. Alright, oh wait. I only have... Let me try, so... So, how do I actually, Nope. Oh. OE did not connect. Okay, yeah. Oh, this is gonna be a lot to do. I don't know if I'm actually gonna be like yeah, I might like finish up before, but yeah. I just wish I had a bitwise buffer. Oh, really? Yeah, yeah, so you're like, so you're, alright, so these 3 bits are the, yeah, so higher bits, which I'll turn, weird I can't turn that specific bit on. Oh, no I can, weird. So yeah. So these 3 bit, alright, those go to this one. That's the read switch, okay, so. That's R1, or no. Yeah, so R0. I'll just put like a pink for now. Alright. And that's the load switch, yeah? Four. Five. And you go to enable. Alright. Yeah, so now that goes to enable. Then then I'll pick another color to do the same over here. So 0, 1, 2, 3, 4, 5, and I've been connecting them all to the same bit. Not what I want. That's the load bit. This is, yeah. This byte is the save byte that I'm currently connecting up. Or save bit, but yeah. Yeah. Then you will be a special one as well. There. Now, more fun times. I'm gonna draw this out all the way to here. If this works, that'll be very cool. Click. All right. Yay! We've got the memory bus. Alright, the bus is a circuit that allows copying data between components. Instead of having every component connect to every other component, connecting individual components only to the bus greatly simplifies circuits. You likely make a bus that looks somewhat like this, connecting input, output, and registers. Good idea to be conceptually aware of the bus. In later levels, a common source of confusion is attempting to carry more than one value on the bus in the same tick. So yeah, yeah. Alright, so yep, here's the bus right now. Yeah. To the map. And we've got a bit more time. Oh, alright, back in the ALU. So now we need to... Alright, more! Alright, so... Yeah, time for more instructions. Now we're gonna have in... add in a sub, so... Can't move that anymore, okay. Alright, so... Add... Sub, okay. So instead of this, I should use a 3-bit decoder. Or Nand. Nor and add. Which I can fit in an add down here, yeah. So add. Whoop. That's 9 o'clock, okay. Switch here. And then a switch here. Oh wait, let's do a switch here instead. Oh, it's mine? Oh no, that's just holding on having a Carolyn. Then I can have a egg. And another add. Just like an add with like a carry flag. Always set. Will be set to track. Wait, is that a sound effect? Yeah, isn't virtual computer redundant? Well, I'm making a computer inside. Oh, that was you clicking your tongue. It's rather satisfying. It is a very satisfying sound, yeah. Probably not great place. So, you go up there. Then I can do the, byte add, yeah. There, then let's add a always on carry bit. No. Subtract is, not correct. Wait, no, that's to get the opposite, not to subtract. To subtract. Okay, yeah, yeah, so. Yeah, alright, for subtract, which I can just do pretty easily, so. Put the switch back here, so. Then we're gonna need an add. Gonna need a subtract, which is going to be a negate, then add with carry flag. No. Because I forgot to link the output. No! Because I swapped the traces. Wait, do I not need that? Alright, looks like we're good. Oh. Yeah, nice, yeah, Alright. I am not, this is a very messy ALU right now. But I've got add, subtract. Alright, now okay, so it is after 9, so I think I am, like, 1, 2, 3, 4, 5. I'm gonna just keep going. I wanna, like, get, like, at least decently far. Circuit you build in the registers level can copy values between registers, while the ALU can do different operations on 2 inputs, but need to be able to do both in the same circuit. To do this, build a decoder which will decide which mode our computer's in based on the 2 bits we haven't used yet. Okay. Single byte instructions, Alright, distinguish, yep. Okay, so immediate, calculate, copy, and condition, ooh. So O, 1, 2, 3, okay. I can just do that with, like, a 3-bit decoder. And a splitter, of course. O, 1, 2, 3. No. Wait. Oh, highest bits, Lemma. One, 2, 3. Circuit's been saved to the component factory. Woo! On words. Conditions. Level has a value input and 3 condition bit inputs. The 3 bits select the condition as shown below. Check the value against the selected condition and output if it's 1 if satisfied, 0 otherwise. Okay. Woohoo! Okay, so alright, so less O, right, yeah, so less O, less equal O. Not equal O, right, always, so. Ooh. Yep. Ah. So. Let's. Yeah, so that is, alright, so 3 bits, so that's a 3-bit decoder again, on a byte splitter. Always is this byte. You can just wire straight to that, okay. Okay, so That's equals O. And, like, just for never, I can just leave that totally so equals O. You have a, you have a piece, two or the whole byte together. I've got, 8 bits to a byte, byte to 8 bits, add 2 bytes, bitwise negate, byte or, byte not, mux, and switch. So, less O is just, like, so I should have a byte splitter here. Less O, because we're talking, 2's complement. Less O is just... is very easy. That's just... Right, so, you know, I'm gonna do color coding again, so... Alright, plain wires for that. Okay, so... Less O... That... is just... And... And I think I'll, like, actually, I should have, like, the bus wire be... there. Alright, so... that is equals 1. Or no, that is equals O. Oh, negator is like, okay, that's why I was getting confused. Oh, so, I can just, for that one, I'll do this in, like, here, so... Actually, I don't want that always split, I think. Then, light blue, UR equals O. So that will just be, like, if you add one and carry flag. So, like, let's say, equals O. Yeah. Or no. No, that's not. Nor, yeah. Subtract and see if it's O. Yeah, that's... if I put a negator? That's equals O. Wait, no, I want not negate. Right? Yeah. Alright, so I've got that, okay. Good. Then number 3 is less than or equal to O. Which I've got less O and equal O, so I can just or that. Oh wait, ooh. No, no, I didn't want that. I wanted a... Where's my buffer? Do I not? I got the buffer. Where is... Why don't I have access to the buffer? Man buffer? Nope. Yeah, just do this. That is effectively a buffer. Alright, so that's good. Then... Always, yep. Not equals O. Yeah. I think your ore buffer was neater. Yeah. So, put that in, then I need an... So... That's not O. What is... Oh. I see the issue. What is, the connection here needs to be buffered. Which I'll just do with, an OR. Also, you're gonna be... that's not O. And something's still going wrong here. I wish I had access to the buffers here, but I apparently don't. So, less than or equal to 0, yeah. So, or I'm on not O right now, so... Oh, I see the issue. I'm hooking too many things up. I forgot to actually check, so... Equals O. Oh, equals O is busted right now because of... Alright, so... You're gonna need an AND. I think, yeah. Oh, no, I don't... You're gonna go there. That I have room to slide up here. That's equals O. Right then, right, so you're gonna need an AND. Print orange, yeah, so bus color. So how are you getting... Oh no, why can't I just have buffers? Yeah, I'm gonna have to do a... I am getting tired and I need to, like, rethink a lot of how I'm doing this. So... So you're always, I'll at least wire you to bus, okay? Oh, thank you for the highlight. Maybe, and the output with the demux condition instead of both? Yeah, I don't have, yeah, I'll look into it, but I need, like, just, my brain is, like, on the, like, at the point of being a bit fried, so, like, I'm just confused why I don't have the buffer. Like, where was the buffer level? Yeah, like... like... Why don't I have... Is it because it's not on that path? Like, I have it here, okay. Alright, so that's to merge the arithmetic engine in and everything. Yeah, not in the path. Yeah, like, just why isn't it in the path? You need it here. Yeah. Oh well. I am, yeah. Not sure you do yet. Yeah, well, like, it would simplify things a lot if I had it, but... You can have the sub-ops running no matter the input and filter the output. Yeah, but like, I have very little space here is the main challenge. Yeah, I'll figure it out another time, because my brain is hurting. Yeah, let's just tag back to just chatting for now. I have been having a lot of fun with this. It is, like, very fun to do. Yeah, that's something. Thank you. Ooh, that's a lot of mess. Yeah, this has been super fun so far. Yeah. Yeah. Like, it is, like, just super cool to have, like, be making my own computer, and I'm definitely gonna be, doing more of this in the future. I might do it on my own time, I'll see. But, yeah, let me, find someone to go raid. Who is live? Right for a while. Ooh, shit, Worm's online. I'm absolutely going over to Worm. Actually, yeah. Internet Worm? Yep. So we're gonna go soft robo raid and a bug raid Internet Worm. Thank you all so very much for watching, hanging out, joining in. This has been very fun. Yeah, a bit quieter, but yeah, like, I have really liked working on this. I cannot wait to do more. Thank you for everyone who dropped by. This will be my last stream of the week. I've got some homework to do now. But yeah, yeah, I'll have a new schedule out soon. When we get over to Worm's channel, please don't forget to drop them a follow, because they are great and awesome and just super cool. Good luck, thank you. But yeah, with that, I am gonna send you all on over there. Let's start this raid in 5, 4, 3, 2, 1. See you soon.